Alrighty then. Welcome, everyone. It is good to see you. There's a Sampi meeting tonight from 5 to 6. There are games and pizzas and information about industry tours. You should be there. Sounds good. All right. So we're going to talk about the service attributes of materials, or the material properties. Either way, I like service attributes a little bit better because it really focuses on the fact that it sets how we can use the material. It also doesn't give you the idea that they're static. So to me, material properties sort of sound static, like there's a property for this material, it has a hardness of 43 Rockwell C, and it's going to stay that way. And that is definitely not true. The material properties move all over the place as we interact with them. So, on the homework, looked through a lot of the homework that you turned in, and a lot of good answers. A few for the first question were a little bit inspecific, so that's okay anyway, but we're learning how to answer them and what is there. So there were a couple of things. So when there were some that said it is the point at which we transfer from elastic stress to plastic stress, but it should be termed pretty carefully as the strength, yield strength is the strength at which, or the stress at which we move from plastic deformation or elastic deformation to plastic deformation. Is the elastic stress consumed? Does it turn into plastic deformation or plastic stress? What happens to it?
I think it turns into it, but I actually had a question about, like, do you have a problem with us, like, writing word for word what you said in the videos for our answers? Like,
no, it's okay.
Cool.
You can write a word for word if you want. You'll find that later on it's easier to just re-say sort of as you want to, but anyway. Okay, so maybe it turns into it. How do other folks feel about that? Yeah.
Well, I just think of it as the point where, like, the deformation caused by the stress becomes irreversible. So
okay.
It seems like it would be like adding on to what was there before, but I'm not sure.
Yeah. Okay.
Like the elasticity is exhausted and then becomes plastic deformation afterwards.
Okay. I like this answer a little bit better because what happens when you let go? What happens when you let go? So if I deform something and then I let go.
After the point of plastic? Or
yeah, after the point of plastic deformation, if I bend it.
You'll almost see like a similar elastic modulus, but you're going to have an offset in that strain. So now it's going to be permanently deformed, like say, I don't know, 0.2 millimeters off from what it normally would be. But you'll notice if you start to apply stress to it again, you'll have a similar elastic modulus where it'll have a similar slope. That's the best way I can describe it. Right?
Yeah. Okay, so I unfortunately don't have anything here that's metal. But I'll use this fine twist tie that I found. So if I bend it, it's elastic, elastic, elastic. Okay, it's starting to be plastic right there. If I let go, it springs back. So the elastic stress does not get converted to plastic. There is still a loading of elastic stress that is in that part, and when you unload it, it will spring back. And actually, you know this intuitively. If you try to bend something, like if you take a paper clip, which is what I was looking for and didn't have, if you take a paper clip and you want to bend it to a 90-degree angle, you will intuitively bend it past 90 degrees and let go and it'll pop back. Or you'll bend it to 90 and you'll let go and it'll open up, and then you'll bend it again and you'll keep going until you get there. So what happens on the graph, if you have your stress strain graph, it goes up in the elastic region It starts out in the plastic, and if I let go, it will come back to a zero stress position here. This, the modulus will stay relatively parallel to the first one. Ideally, it would stay exactly parallel, but materials aren't ideal. And so it won't be quite exactly the same because there's other stuff that happens that goes on, but ideally it would come back. And then if you wanted to load it again, you would load it back up this curve, and then it would continue on the elastic plastic stress, or the plastic strain curve, just the way it was going to before. And some things to note, you have to work harder the second time. So it takes more stress in the part before you get back to where you are plastically changing it the second time. Okay. So now I know that a lot of your answers in that are just wording, right? It's just a wording issue, but I want you to be careful with the wording. It's kind of odd, frankly, that after taking an entire materials class, and the other materials classes, we have a class that's essentially just on stress, strain, and strength. And you're like, oh goodness, I understand this. But the problem is we have to really understand it. We have to know it. And we're working in a different place than we normally do. So when you do most of design, we stay down here on the elastic part of the curve, because we don't want parts to fail. In general, we will do all of our design down there. But in manufacturing, we spend all of our time out here. And frankly, this portion of the curve is a bit of a pain. So if we could just stay in the plastic region, life would be good, but we can't, because we need to release things and they go back to zero stress. So we're always having to deal with this portion of the curve, but we're gonna spend time up here. That's complicated, right? Because as a number of you noted in your explanations, yeah, this part down here in the elastic region is all linear and nice and easy to predict, and it's easy to understand. And when you get out here, messy stuff happens. And that's where we're gonna be. We're gonna live in the messy stuff. Why do they define this as a 0.2% offset from the line? They've got a perfectly good line. Were they just being cantankerous that day that they said, I'm gonna choose this spot right there instead of that one that's got this 0.2% offset? Why do you think that 0.2 offset's there?
Gives you something you can measure, right? Like if you're like any deviation from the line, you know, you're getting real data. You're going to have some amount of deviation from your slope, right? You can get an average slope, but you're going to have some deviation. And so if you have a defined 0.02 or 0.2% deviation as like, okay, well that's when it actually starts moving in a meaningful way, right?
That's right.
That's when our slope starts moving.
Okay.
Instead of just varying a little bit.
That's right. Because in the book, these look like nice straight lines. In real life, they are not. In real life, it wiggles as it goes up here and different things happen within the material. And this is just saying, okay, we have now deviated enough from that nearly linear portion that we're gonna say, yes, at this point, we have moved into the plastic region. And especially right up here at the top, a lot of things happen as it is moving into the plastic region, lots of little wiggles and whatever. So it'd be very hard to define it. This is just a little easier to define. You can take an average of this entire line, and then you can offset it by 0.2% and figure out where it's going to be. What other strengths are there besides elastic? We talk about. Sorry?
Tensile?
Okay, so tensile is a stress. That's how we're loading it. You were meaning to say, go a little bit further, has another word with it. Where you mean?
Strength.
Yeah, okay.
Ultimate.
Ultimate tensile.
Oh my.
Yeah, so ultimate tensile strength. Tensile just says which way we're loading it, because this is the tensile yield if we're loading it in tension. This is the tensile fracture strength. So yes, the ultimate strength and the fracture strength. What is weird about the ultimate tensile strength? Anything that you think of that's weird about it? Yeah.
So the point on the graph where it starts to like go down doesn't really make sense because it's like you're putting less force in, but it's performing more.
Yeah. So it is odd. So it comes from the engineering stress strain graph, and it's odd because it sort of exists and it kind of doesn't exist. It's sort of a weird. It sort of exists because we're mismeasuring the part. Right? If we were doing a true stress strain graph, it just continues going on. There is no ultimate tensile strength that you can measure. But on an engineering stress strain graph, it gets to this point that's high, and the highest point, and then it starts to drop off. What happens in the sample, you have this sample, and you're pulling this sample, and it will get a little thinner and a little thinner and a little thinner, and then all of a sudden it will start to neck down right here. So the area, cross-sectional area, starts to change very rapidly at the ultimate tensile strength. What is bizarre about the fact that the ultimate tensile strength kind of doesn't exist is that it is super useful. There are so many things that utilize the ultimate tensile strength in formulas, in understanding of different processes. You can use it to estimate failure. You can use it for just a ton of things. If you're doing machine design, you use it just constantly. In the design of shafts and the design of bearings and all these things, it just comes up all the time. And it's weird that it does, because it's kind of an imaginary number-ish. It's a real phenomenon, but it's kind of an odd thing. So between engineering stress and true stress, which will be higher? About 50% of you got this backwards. You were thinking about it the right way, but just forgot that. In tensile stress, you can think of the stress as being the force divided by the area. So if the area stays large the whole time, then this number stays small. But if you do the true stress, true strain, and you're actually measuring this area, then as this area gets smaller, the stress of the material will go up. And that's why the true stress, true strain continues to rise. So true stress, true strain will mostly always be above the engineering stress and strain. It is a little bit odd because the strain is measured differently. It's not quite the same number for strain, but the curve will still be higher for tensile loading. There was some folks noted, well, maybe this is backwards in compressive loading. And the thing is, we just don't worry about it in compressive loading, because in compressive loading, it doesn't neck down. And stuff, once you get to plastic compressive loading, just goes totally berserk. And so it fails in odd ways.
So is it ever lower than the engineering one?
I don't think so.
Okay.
There's a possibility that right in here it is, because the way that the strain is measured is different, but it is essentially above. Yes?
Just for notation purposes, on those slides when you did the stress, like for true stress, you wrote true under it. Do we
Yes.
normally do like the O symbol and then like T, or do we always have to write true, or is that not really going to be a problem?
It's not going to be a problem for what we're doing. We'll just talk about it. What you would normally do, well, yeah, you could put a true under it or something like that. Yeah.
Okay.
Every textbook has different nomenclature, just to make life hard. What is hardness and how is it tested? People did fairly well on that. It's the resistance to indentation and scratching. So how do you test it? You indent it and you scratch it. And so that is what you actually do on the shop floor. So if somebody comes in, for instance, do you remember last year there was a very large crane building the electrical and computer engineering building? In the middle of Christmas vacation, when they were setting up that crane last year, one day all these people trooped into the manufacturing lab down there and they said, "Where's Ben?" I said, "Ben's on vacation. Can I help you?" And they said, "We need this to be smaller." And they handed me a pen. And I said, "Okay. Why do we need this to be smaller?" "Because the crane won't go together." So it was one of the pins at the, so the crane had a big boom and then it had a sub boom on the end. And it had two pins that joined the two booms together. And it was one of those pins that they had gotten a new one and it was the wrong size and they needed it smaller. And they said, "Can you do it?" And so the first thing that I said was, "I don't know if I want to do it." I said, "If I'm going to do this, I want a letter from the crane company, and I want a letter from the construction company, and I want a letter from Western saying that it's okay for me to do this, understanding that I have no drawings and I have no way to test, I have no specifications of the hardness or the surface finish required." They're like, "It's okay. We have, I can't remember what they had. It was, the crane rental was like $10,000 a day or something. It was very high, and they had a huge number of people on site to build that crane. And if they couldn't build it, it was gonna cost them several weeks of delay. So anyway, the next thing that I had to do was say, well, is it hard? Is it hardened on the outside? Because a lot of times something like that would be hardened on the outside. And they didn't know. And so what I did was pick up a file and then run the file across it sideways on edge. And I could scratch it. So because I could scratch it with a file, I know that it's not hardened. And to me that matters, because if it's not hardened, then I can turn it on a lathe. If it is hardened, then I have to use a grinder to be able to cut it. So anyway, yeah, unfortunately it was not hardened, so I was able to do it. So the whole crane, every day when I walked into campus from 12G, I'm like, "It's still up there." Guess that's good. When they took it down, I asked them for the pin, and I said, "I would really like to have that pin somewhat for, you know, just remembering that that we did that, and somewhat because I don't want it going anywhere else." And they said, "Nope, we got to use the pin next week." And I'm like, la, 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 la. So anyway, that was interesting, but it stayed up and nobody died. So
You made their day. There was a machine shop on site.
I know. It was nerve-wracking because there were like 8 people standing there in their little construction vest watching me as I machined it. We all understand that I haven't done it with this material before. I have no drawings. It's all good, right? So anyway, it was interesting. The amount of energy per unit volume that a material can absorb before failure is the toughness. Toughness, yes, good. Toughness. So that is impact. We're thinking about impact when we're thinking about toughness, and it being able to absorb that rather than just shattering. An applied force to a material distributed across an area. Stress, good. Resistance to scratching or indentation, we just talked about. Hardness, great. The amount of stress applied to a material that affects some change. Strength, that's right. We get to a strength when it affects some change. And the amount of strain applied to a material before failure. Sorry.
Failure strain?
It's got a bit of a different name to it. It's a funny name because it's kind of backwards. Yes?
Ductility?
Ductility, that's right. It is the ductility. I also in the slides once called it the brittleness, brittleness is a characteristic. It is not a machine property or a material property. Ductility is the material property. Yes.
Is brittleness not just a lack of ductility?
Yeah, it is. So they're the inverse of each other, but you don't ever measure brittleness.
Could you just measure low ductility though?
People talk about it being a brittle material, but the material property that you measure is the ductility. When you talk about the ductility. Yeah.
Will the slides be posted?
Yes, so well, both are true. The slides will be posted for this year's slides. They are posted for last year's slides. So it's on the Canvas site. If you go to Pages and then Section 2, Page 2 is PowerPoint and whatever. And I will replace last year's slides with this year's slides after class. Each day. Yep. All right. Engineering stress and strain are A, not important because they do not accurately account for a decrease in cross-sectional area. B, the best choice for solving engineering problems. C, important for showing material behavior in the elastic region. Or D, useful for predicting material behavior in the plastic region.
Is it C or D? I was between the
I
two.
thought it was
I was
D.
gonna ask Alexa.
Because it predicts, like the ultimate tensile strength.
So
is
wasn't
only in the
true
plastic
the one
region.
that doesn't bend, like start going down, and that was.
Well, because you can't use engineering stress for a behavior after the plastic region because then the cross-section areas.
But elastic is
But
first,
it's helpful.
right?
Yeah, so-
Elastic, then
So
plastic.
could you do the, I was thinking you would do it for the elastic region because it's more predictable, but then.
So I think this is the difficulty, right? Because what is the best answer? The best answer is that it gives us the elastic region because it gives us Young's modulus. So that is the best answer overall because Young's modulus is the most important thing that we can learn for a material. And that's because almost all design happens in the elastic region because we don't want stuff to bend. When do we want stuff to bend, or when do we go past the elastic region?
Manufacturing.
Sorry?
Manufacturing.
Well, yes. Okay. When in design do we go past the elastic?
When you have sacrificial parts that you're either planning to replace or sacrificing so that your more expensive or problematic parts don't break instead.
Okay, yeah, so if you're doing energy absorption for some reason, so the bumper and all of the frame structure on a vehicle, they design into the plastic region because they're trying to protect the people inside, right? And so you sacrifice all of that structure to protect the people inside. And so they will do that design there. Sometimes with other materials you will as well. You will have something that breaks to protect the important part. And so that happens. So is it useful for predicting material behavior in the plastic region? It is, as far as giving you the ultimate tensile strength. Beyond that, it's a bit of a misnomer. So it's better to use true stress, true strain. But we don't very often. Why don't we use true stress, true strain very often?
You have to measure like the area constantly.
Yeah, it's just harder. It takes a much more capable setup to be measuring the cross-sectional area. And in fact, all the systems that do it don't actually measure the cross-sectional area. They have little lasers and they look at the diameter and then they assume that it is deforming uniformly. So there's a lot of assumption going on in that because you have no idea whether it's deforming uniformly or not. That's impossible to say. Okay. What is the constancy of volume?
The volume of something stays the same.
The volume of something stays the same. We're not creating or destroying material. What assumptions are in there? Yeah.
The material is fully dense.
Okay, yeah, so we have to assume that the material's fully dense before we start. And we assume that we're not creating energy. So that's okay. That's good. All right. Whoa, that's backwards. How are animation gone awry? How are ductility measurements reported? Yes.
Percentages of elongation
Okay, percent elongation is one.
and reduction of area.
Percent reduction in area. Are the two equivalent?
No.
They are not equivalent, and you cannot get from one to the other. So if you are working in one and you read a paper that has the other, you cannot get anything other than anecdotal sorts of information from that data. You have to have consistent data to be able to compare ductility. It's kind of a pain, actually. Wow. All right. So a poll. Do you think, A, that you apply a stress to achieve a strain? B, that you apply a strain to impart a stress? Or C, you can do either depending on the situation? Okay.
Is this like a hold it
A,
up type
a
of
C.
Do we ever like?
We could do A, B, we could do 1, 2, or 3. Okay, so a lot of ones. So the thing is, in most cases, we do impart a stress to achieve a strain. In most cases, but not always. So there are materials like piezoelectric crystals. So in a piezoelectric crystal, if you put a voltage across the crystal, it will strain the crystal. It will change the shape of the crystal. That imparts a stress on the system, but it is actually a shape change that is happening because of, yeah, it is a shape change that is happening, and then a stress comes from that. Similarly, there are some materials where a thermal change will change the shape. That becomes a stress as it is either prevented from changing shape or it deflects. But the shape change comes from another input, chemical, thermal, electrical, typically. So C is the best answer. We are not going to go through these because we have just done those. So, oh, except for the next to last one. What is bad about a process that leaves surface cracks?
It makes it easier, right? Like it causes a deformation of part and continuous spread.
Okay, so it causes a little weakness that can spread, especially under what conditions?
Isn't it like cold?
So cold, thermal can do it, yeah, just with putting a stress on it.
I wrote surface defects reduce the ductility of materials.
Okay, so they reduce the ductility, it will fracture at a lower strength, or a lower amount of strain. Yeah, so it is bad in tensile loading. So it doesn't matter much in compressive loading, but if that area is loaded in tension, then it has the opportunity for that crack to propagate, and it's really bad in oscillating conditions. So if you have an airplane wing that's out there going up and down over every little bump in the atmosphere, it will oscillate. If you have the suspension on a car and it's oscillating up and down all the time, in flexing, that will cause a failure. So there's a process called electrodischarge machining that we're going to talk about a lot later in the quarter. And electrodischarge machining uses a high voltage from electrode to the material, and this spark starts to jump across, and that spark is so hot that it creates plasma and it just explodes the material away. Now this is on a very, very small scale, but it explodes the material away and it melts the material, and then the material refreezes to the surface, a small portion of it. And when it refreezes to the surface, because it is a liquid, the surface tension draws it into a little sphere. So it draws into a sphere and refreezes to the surface. And then the next little spark happens and another little sphere appears right next to it as it's machining material away. So in between two spheres is a very sharp crack. And so that crack can then propagate through the material if you oscillate the material. So people in the aviation industry were super excited when electrodischarge machining came out because it is, does not matter how hard the material is. It machines exactly the same. The melting temperature of the material matters, but how hard the material is completely irrelevant. And so when this was a new process, they were trying to do a lot of machining of titanium to make light parts for big planes. And so they were very excited about it. They used it. They launched a bunch of planes that had parts that had been made on wire EDM, and they failed. And they failed because of this surface finish. And so all of a sudden they said, nope, we're never using wire EDM again. Just not gonna do it. It's not worth the risk. Turns out you can do processes to remove that surface finish because it's only on the surface, and you can remove that surface finish and then you can use the parts. But it's taken a long time for that industry to come back to being willing to even consider electrodischarge machining because of that. Is it better or worse? So is a surface crack better or worse than a machining process that leaves a visible mark on the surface?
Probably worse.
I would say worse.
Worse. Why?
I feel like a surface crack, if it was made for being used, that's like where it was already weakest. So then it's going to continue to
Okay.
get worse. The random mark might not be where the material is already weakest or being
Okay.
stressed the most.
Okay. Other thoughts? Anybody? I mean, in a understanding sort of mechanism, that's true. Does anybody agree? Yeah.
Maybe like depends on the application, like what you want the part for. Like maybe you need a really smooth finish, and it doesn't matter so much. Like depends on.
Okay. Well, it does. That's true. It does depend a little bit on the application and whether it's going to be loaded in any kind of oscillation or not. It turns out that almost always surface cracks are worse, and that is because their radius is smaller. So the tooling marks on the surface, because they're visible, their radius there is pretty big. So on surface cracks, or on any cracks, the crack is more likely to propagate if the radius is small or if the crack is long. If your windshield has cracked, you know this, because it had a star, plus a 1/4 inch, it had a star plus a 1/2 inch, and bam, it's all the way across the windshield. What happened there? That stress rose as it got a little longer, and then it failed all the way across the windshield. Yes?
Why is the smaller radius more likely to?
Because it is
grow again?
focusing the stress at a very small location, and so the stress goes towards infinity. Yeah.
I got a bullseye crack on my windshield the other day, and I was like, it's the end of the world, but maybe it's not because it's big.
What you should do is you should take it, and if it's not, it depends on how big it is, whether they'll do it or not, but you should take it to the windshield place, and for a small amount of money, they will drill the end of every crack.
Really?
And so what they do,
That's cool.
it costs, most insurance will cover it, and even if the insurance doesn't cover it, it usually costs like 15 or 20 bucks. But you have this little crack that looks something like that, And what they do is they come in and they drill a hole there and there and there and there and there and there, and then they fill them with epoxy. And what they are doing is they're taking this very sharp radius and they're giving it a huge radius, the size of the drill bit. And then it won't propagate anymore because they made that radius larger. Now, if it's a really big one, I can't remember what the number is, it's like 3/4 of an inch or something, then they won't do it because they'd rather sell you a windshield
like
or
this big.
something, I don't know.
No, that was, I think I was just looking, it's not that big.
Anyway, so
Doesn't look
this
like
is
that.
practical, it's real, it happens.
Cool.
It's nice, look at this. Class was useful, thank you. Okay, we're gonna talk about what happens when the parts fail, or we're gonna watch this person who's gonna tell us what happens when the parts fail. Because it's not really clear, right? You're pulling on this part, you pull, you pull, you pull, you pull, it fails. Why? That's weird. So anyway, let's, if I can find my mouse, change something, let's see if this works.
Metals. They're all around us. If we knew more about the way metals broke, then the structures of the future could be safer, more efficient, and even less expensive. Hi, I'm Jeffrey Balmer, and I devote my time to finding out how and when metals fail. Did you know that every block of metal has tons of microscopic voids inside it? And that these microscopic voids actually play a crucial role in failure. When the metal is stretched or loaded, these voids start to grow and link together until the metal fails. If we look at a copper bar being pulled in tension, we see that it behaves the same. In the center region, it necks down until eventually it fails. Now you might ask, what about those voids? How do we know they are the reason for failure? Well, one way we know is by looking closely at the fractured surface. The surface has many dimples, which is a sign that voids have grown and linked together. Now, if we zoomed in on a chunk of metal, it might look like this. If I zoomed in the same amount on a human hair, it would look like this. But if I wanted to analyze this chunk of metal, it would be quite difficult, because there are many voids and they're all scattered randomly. In my work, I look at one void at a time, and using a computational model, I look at how it responds to many different loads. I am then able to stitch together the responses of individual voids to understand how the metal will behave on a much larger scale. The simulation you see here is another tension test, where this notch bar is pulled until it fails. One of the very useful things about computational simulations is that we are able to look inside the material to see how the failure process occurs. You can see here that failure occurs as a crack that starts at the center of the member and propagates outward. So, by using a bunch of models of microscopic voids, I'm able to make predictions about how and when larger elements will fail. The truly amazing thing is that these predictions actually correspond to experiments. I'm able to show that damage starts to occur in the center of this element and leads to a crack, which is the same as seen in experiments. The use of computational models such as mine, when combined with simple experiments, will help improve our ability to predict cracks and ultimately help to avoid the failure of our structures. So, as we move into the future, our use of metals will be increasing in efficiency, economy, and safety.
Okay.
If you like my video and want to learn
That
more,
was
check out.
great, Jeff, thanks. We appreciate your video. When you hear them talk about doing failure analysis on something, and they say it failed in fatigue after 50,000 cycles, or they say it just failed because of overloading. The way that they know that, when they go and they scrape up a plane crash or whatever, and they start looking at the parts, is they look at the surfaces that broke, and they look for this ductile dimple failure. So this is a failure that happened in a ductile material, and if it has the little ductile dimple shape to it all over, that means that the part just got overloaded and it failed. If it fails in a brittle mode, so it's not ductile anymore, the material was too hard or some other thing that caused it to fail, it will not have this surface. It's a lot smoother and it will just be gone. And it also fails on 45-degree angles in shear. And if it is something that worked its way until it failed, what it will look like is it will have this surface on some of it, and then on part of it, it will all be mashed flat. And that's because the crack is propagating along the surface, but as it's propagating along, the thing is still working back and forth, and so it keeps mashing down the new ductile dimple until it finally fails in the end. And so when they do crash analysis or they do failure analysis of something, that's the surfaces that they're looking at, and that's how they determine a lot of what was a failure mechanism. Yes?
I don't know if you know this, but is there AI that can do what that dude does?
Is there AI? So there's AI that can evaluate it, but the prediction is very, very difficult. And so AI can be used as a tool in helping to do that, but that field you have to do lots and lots of different solutions, and then you gang those solutions together and you use stochastic methods to
What are stochastic methods?
Like with probability. So using probability to determine, so he looked at some of them are gonna fail this way and some this way and some this way, and then you use probability to determine how many of each of those kinds of failures you're gonna put in there. And anyway, so AI can be a tool in it, but it can't do it. Now, AI can probably help with looking at surfaces and determining exactly how it failed, because it's pretty good at looking for patterns. Though humans are still really good at looking for patterns. Anyway, 5-minute break, so be here at 10 till.
No!
It just ended. I'm late. Guatemala?
Okay, we're gonna go ahead and start again. Compressive strength. Compressive strength is bizarre. So, it is hard to find information on the compressive strength of most materials. And that is because most materials don't fail in compression. So they may have a compressive elastic response. As you squeeze them, they will start to barrel, they will bow out at the sides, they will, the cross-section will increase. But when you actually get to the point of starting to plastically deform them, they don't fail by compression. They fail in shear. So what happens is they will shear off at a 45-degree angle and the material will slide sideways. So it's a different failure mechanism. So there will be a shear strength of materials that you can look up, but for most materials, it's very hard to find a compressive strength. The place that you can find a compressive strength is for materials that are brittle. And so glass and ceramics, you can find a compressive strength. But anything that's squishy at all, you can't. Just as a point, we've talked about tensile, where we pull on the material and it gets thinner, and then on compression, where you squash the material and it gets wider. Are there any materials where you squash it and it gets narrower?
There are.
Okay. What is one of them?
Don't ask, I don't remember. But I know there are.
Yeah, there are. So one of the most, yes?
Oh, I was just gonna guess if it's a non-Newtonian fluid.
Well, we're talking about solids, so
Okay, yeah.
Yes,
But
non-Newtonian fluids do weird stuff. Yes, I agree. So cork is the one that you deal with the most. And so it's why we use cork for the things that we use it for. When you take a cork and you put it in a bottle, you mash on the end, and when you do that, it actually reduces the diameter so that it goes further in the bottle, and then when you release that stress, the diameter increases, which holds it in the bottle. And a corkscrew screws down to the bottom of the cork, and then when you pull it out, what it is doing is compressing it to make it smaller. Yes?
How?
How? It is in the structure of the material. It's because it is a grown material. It comes from cork oaks, mostly in Portugal. And it is just the structure, the internal structure of that when you stress it in one direction, it moves the alternate way in the other direction. And it doesn't violate the constancy of volume because it is not a fully dense material. The structure has space in there. It's also why cork boards work, where you put push pins in them. When you push it in, you're applying the stress, it kind of moves out of the way, and then when you release the stress, it re-expands and it grabs the end of the pin. If you ever go to Portugal, you'll see all these trees with numbers written on the side between 1 and 10, or actually it's 1 and 0. And that is because you can harvest the bark of a cork oak every 10 years. And so they have a big number written on the side, which was the date of the last harvest. So 2024 will all have 4s written on the side. And they take it and they just, they carve around the top and the bottom of the trunk, and then one slice down the side, and they just peel off about 1 inch thick of cork. And then they throw it in the back of a truck and drive it to a cork plant. And it's interesting, the rise of plastic wine bottle stoppers has had quite an effect on the industry there, and so they've been working on other things that you can use with cork. So it's really funny if you go there, all of the tourist shops are full of everything cork. So they have cork book covers, they have lots of Birkenstocks because of the cork sole. They have corkinis, which are cork bikinis. It's an odd set of stuff. There was a cork wedding dress at one of them. It was just all kinds of things cork.
Was it weird?
You have to really want to do cork, I guess.
It's right, they would get really old.
All right.
Like they get really
So we're going to talk about temperature now, because temperature is super important to what we're doing, both from a good aspect and from a bad aspect. So if I have a material that has a relatively high strength over here on the left side of the graph, the x-axis of this graph is in melting temperature. And so if I'm over on the 0 end, I'm on 0 times melting temperature. And if I'm over on the right end at 1, it means I have reached the melting temperature. So you can think of it as sort of tenths of a melting temperature or whatever. Anyway, so as I increase towards the melting temperature, you can see that the strength of a metal drops way off. And so right here, by half the melting temperature, we've lost half the strength of the metal. And then it kind of tapers off towards the point at which it's molten, at which it has no strength at all. Yes?
Is by the half the melting temperature, half the strength is gone? Is that like an actual thing, or just?
No, it's not an actual thing. It's that's what it looks like to me on this particular graph. Yeah, it is not something that you should not take that to the bank. No. Now, if you look at the ductility, a material which has some amount of ductility, remember ductility is the amount that I can change its shape before it fails. And so when I get kind of to the same area, or even beyond, all of a sudden this material became chewing gum or silly putty. I can stretch it way out. No, it's not silly putty because silly putty is a different material, whatever. Anyway, so it can stretch way out. So that's pretty cool. So we have three regions that we talk about a lot in metal manufacturing. And the first is the cold region. So in the cold region, we have high strength and low ductility in comparison. We have the hot region. The hot region, we have low strength, we have high ductility, and weirdly, we have higher strength if we're changing the shape faster. So the rate at which we change the shape matters in the hot region. Okay, we'll talk about all this later and why it matters. So we're going to define cold as less than 30% of the melt temperature. So it is the area where this is fairly linear and fairly level. So there's not much strength change between 0 and 0.3 times the melt temperature. A little bit, but not very much. We're going to define the hot region as above half the melting temperature. So there isn't anything linear or not changing up there. And then we're going to define this area in the middle between 0.3 and 0.5 as the warm region. Okay. So in metals manufacturing, we're going to do a lot of processes in the cold region. We're going to do a lot of processes in the hot region. And we're going to do nothing at all in the warm region. Actually, they're starting to do a few things in the warm region, but in general, they do not do much in the warm region at all. Can you think of some reasons that we might not want to work in the warm region?
Less predictable.
Less predictable.
If it's
Things,
either hot or cold.
yeah, things are changing super quickly in the warm region. And so a tiny temperature change is a drastic change in the strength that you're trying to deal with. So all of a sudden, I don't know if I'm going to have to squeeze this a little or squeeze this a lot. I don't have much way to predict it, and tiny temperature changes are making that difference. So we don't do much work in the warm region because of that. We do a lot of work in the cold region. There are some really neat things that happen there. We do a lot of work in the hot region. Good things happen there too. And then we go back and forth a lot. Questions about any of that? Okay, some final material properties. We're going this quick, residual stress right now. So if I have a stick, it's a nicely colored PowerPoint art stick, clearly. And I have a hot end and a cold end. What do you think determines how fast the heat will flow from the hot end to the cold end?
Depends on the material.
Okay, the material, what about the material?
Heat conductivity.
Conductivity, okay, conductivity, yes. Absolutely. What else does it depend on?
Mass.
The mass. The rate at which the heat, kind of. Yes, but we work it through a different path first. So how long it takes to warm the end up absolutely depends on the mass. But how fast the heat flows, not quite as much.
The density?
The density. We're assuming fully dense.
Oh,
It does depend on the density, but we're going to assume fully dense metal. Yeah.
The length or width of volume of the thing itself.
I like your first answer better.
The length?
The length, so the distance between T1 and T2, and the cross-sectional area. And so the volume is important, but separating those two is good. Yeah.
I was just gonna say like the values of T1 and T2.
Okay, the values of T1 and T2, how much they differ. Okay, so that is true. So the thermal conductivity, how fast the heat flows from one location to the other, is this equation. It has K, which is the thermal conductivity of the material. It has A, which is the cross-sectional area. and then it has the change in temperature from one end to the other, and then in the denominator it has the distance from one end to the other. So that's the distance in the direction of heat transfer. What's pretty cool is that you may have seen this. So here is one of our cooking pots, and down here at the area that has the highest stress, okay, this is the worst possible place to take away mass from a stress point of view. There are all these holes in the handle, and it looks like they did it on purpose. What are they doing there? Why are there all those holes in the handle?
I think a heat sink. You're trying to dissipate the heat as quickly as you can get to the moving part of the handle.
Okay, so trying to dissipate the heat.
You also heat up quicker.
So to dissipate the heat, we would take the handle and we would increase the mass and we would increase the surface area. That would dissipate the heat. We're doing something else right now a little bit.
Reducing the cross-sectional area?
Yeah. So by choking the cross-sectional area, we don't allow the heat to even come out to the handle. We slow down the rate of heat flow such that this handle is plenty enough mass to absorb the heat and dissipate the heat by convection and radiation, and that way we can grab this metal handle over here, and it will also help to keep the heat in the pot, in the pan at the same time. So we see this all the time, that there will be a reduction in cross-sectional area. Now, why am I talking about this? We are going to find in manufacturing processes that sometimes we try to keep the heat in something, or sometimes we try to get the heat out of something. And so we should just remember that if we have a higher temperature difference or a larger cross-sectional area or a smaller distance between the two, then heat will flow better. Thermal conductivity, let's see, that's what we just did. Now, two other concepts to understand and to remember. One of these is sensible heating, and so that is the amount of energy that it takes to heat up a material is equal to its mass times this weird thing called the specific heat times the temperature change that we want to achieve. So specific heat is joules per kilogram per degree Celsius. How much energy per mass do I have to put in to change it 1 degree Celsius? Any idea what material has the highest specific heat? Water. Water is the highest specific heat. So that's why in the olden times, if they were going to go places in their carriage or their sleigh in the winter, they would heat up potatoes. It's why the potatoes burn you when they come out of the microwave, if you microwave your potatoes, or when they come out of the oven, a long time after you finish cooking them. It's also why they take so darn long to cook. It's because they have this huge amount of water in them, and it takes a bunch of energy to heat that up. It's also why most of our electricity is produced by processes that utilize steam, because by heating that steam, doing the phase change and then just loading it full of energy, you can load it full of a lot of energy and then extract that energy back out to do something like turn a generator. When I worked in the solar thermal energy storage, so what we did was we used high temperature salts that melted at 600 Fahrenheit and between there and 1200 Fahrenheit. We would heat them up using the heat energy of the sun, and then we would store it in the big tank, and then you can pull it out of the big tank and use that to heat water that you can then run through a generator to make steam. or through a turbine to a generator steam. And one thing that happened every 2 years at a conference is that, I'll get you in just a minute, is that somebody would show up in the conference and they would say, I have solved the problem. It's hard to get heat into and out of molten salt just because it doesn't conduct very well, has a very low conductivity. And so every year somebody would show up and say, I put carbon nanotubes in this and it works great. The heat just flows in and flows out, and I will prove it to you with this graph. And they would put a graph up. And what happened is, to put carbon nanotubes in something, you have to suspend them in something. And so they would suspend them in water, which is the easiest thing to use, and they would put that into the salt, and then they would heat it up to 100 C, believing that they had evaporated out the water at 100 C, but it doesn't evaporate out because it chemically binds to the salt, and so you have to go to 300 C to get the water out. And then they would take data and they would show that the salt had better conductivity and it held more heat than it did previously. And it was always because they had water in it that they hadn't gotten rid of. So every year at a conference, somebody would show up and prove that water still has the highest heat content of any material. Happened over and over.
Oh, you just answered it in that last part. It's highest heat content.
Highest heat content,
Okay.
the highest specific heat, yes, of any material. All right, the other heating that we need to talk about, some is latent heating or phase change. So phase change depends on the mass times this thing called the heat of fusion. And so that is how many joules per kilogram it takes to heat the material up. Notice that there is no temperature change in this equation. Why is there no temperature change? Do we not care about the temperature change?
Phase change is not off temperature, it just does it.
Okay, so the phase change happens at a specific temperature-ish.
Yeah, it just happens.
I mean, in textbooks, it happens at a specific temperature. In real life, it happens over a range, but real life is so complicated. So anyway, there is one of these when it changes from solid to liquid and one when it changes from liquid to vapor. Very often, when we take a material and we heat it up to its melting point and then we take it through its melting point, those amounts of energy will be order of magnitude the same. Not exactly the same. Usually heating it up to the melting point takes maybe 1.5 times as much energy, but order of magnitude, it is the same amount of energy just to melt the material as it is to do all of the work to getting it to the melting temperature, or to get it to the boiling temperature and then the amount of energy to boil it. And then the last thermal thing to think about is this. The thermal expansion of something, of a material, is this thing called the coefficient of thermal expansion, which is a material property, times the original length of the material times the temperature change. So if you have a longer item and you change the temperature, it will grow more. It's not very surprising. If you have an item and you change the temperature more, it will change its length more. And then we have the coefficient of thermal expansion at the beginning, which says things like copper and aluminum will change a lot in their length, and things like zerodur and other ceramics will change very little. So it just depends on the materials. In general, materials that conduct heat well also conduct electricity well and also have large thermal expansions and often lower melting points. Not always true, but just kind of as a first guess, If it conducts electricity well, it will probably conduct heat well, it will probably have a large thermal expansion, and probably be on the lower end of the melting temperatures for the material. Questions about any of those? Yes?
Can you say that one more time?
Yes, I can say that one more time. So in general, materials that have higher electrical conductivities will have higher thermal conductivities. They will have greater thermal expansion, and they will have a lower melting point. Often that also means that they will have a lower heat of fusion, and they will have a lower specific heat. Again, this is not universal. It is just, in general, looking at materials. They probably also have a, I don't know if I want to go there. Order of magnitude, they also have a lower yield strength. But again, not universal. Okay, that's excellent. There's a cursor here somewhere. One of these screens has a cursor. I know it. Okay. Well, we'll do one last lab thing before we go to a worksheet. All right, so totally changing. Woo! New brain. If you are in the lab and you are talking to a machinist who machines in inches, this number, 0.001, yes, is a thou, or 1/1000th of an inch. Okay, that's not surprising. This seems like a good system. It will not. People also call it a mil. Please don't ever call it a mil, because the people who work in metric also call things mils, meaning millimeters, and then people get confused and they start fights, and don't ever want to start a shop fight. So anyway, 1/1000th. I don't think it really starts fights. This number, yes?
Can I guess?
You can guess.
Is it a hun?
A hun? It looks like it could be a hun or a hundredth, but in fact we don't. We stay in thousandths, and so this is 10/1000ths of an inch. So why do we do that? Why do we stay in thousandths? We do it because a lot of machine tools, this is kind of the realm where they work really well. They can cut thousandths all day long. And so talking about things in thousandths is talking about them right in their area of capability. And so it's just an easy way to keep track of it. This number?
100,000.
Yeah, so this one looks like it ought to be a tenth, and it is definitely not a tenth of an inch. I mean, it is a tenth of an inch, but in the shop, we're never going to admit that. So this should be 100,000ths. And you should always talk about it as 100,000ths. This is the biggest area of confusion.
Is there not a nickname? Like, do people say?
No,
Honey
they
thou?
say 100,000ths. This number right here, so 0.0001 in most shops will be a tenth. So this is 1/10,000th of an inch. This is brutal, right? This is bad. But anyway, 1/10. And it's because they are talking in thousandths. So it is a tenth of a thousandth of an inch. And so this, again, 1/10 is sort of getting to be hard in most machine tools, to hold it all day long. 1/10 is kind of in there in that realm of, well, we're gonna have to work on that. We're gonna have to be real careful with our thermal control. We're gonna have to warm up the machine before we use it. We're gonna have to not let the coolant get super hot, all kinds of things like that. This number, oh, the possibilities are just endless.
100.
It could be 1/100th of a tenth of a that would be,
Tenth
oh.
of a tenth.
Yeah, but it isn't. So it turns out when you get to this is outside of the thousandths category. And so this is a different set of machine tools. And so this becomes 10 millionths. And in fact, if you are in a shop that deals in millions, then the one right above it, which we called the tenth before, becomes 100 millionths. If you are working in that sort of machine shop. There are not so many of those machine shops, and it may just be some processes, like grinding can do millionths, surface finish is often in millions. So if we want 1/4 of an inch, you can call it 1/4 of an inch, but it can also be 250 thousandths. One reason that we leave it as 250 is because then we can do math more easily. If we start going to 1/4 and then you have to add 14 thousandths to it, then it starts to get confusing. 250 plus 14 is pretty quick and easy to think about. And so we will often just always think in thousandths of shop. Questions about that? All right. So I have a worksheet here for you to work on, and we will discuss in just a minute, not in just a minute, in a while. And what I want you to do is, it has a list of material service attributes that we've talked about today. And it has three different operations. One is the screw of an injection molding machine. One is extrusion. So in extrusion, metal extrusion, we take a large amount of material, metal, and we shove it through a little tiny shaped hole, and it comes out as whatever shape we want it to be. Much of the world is extruded. So the all of these edges around these are probably extruded. This room doesn't have a crash bar on the door. The thing on the crash bar on the door is usually extruded. The chalk trays are all extruded. The thing up at the top that has the cork in it, that's an extruded piece of aluminum. So that's made with a die that has that shape. You shove a lot of aluminum through a little tiny hole and it will come out in hundreds of feet of that. Very cheaply, very inexpensively, and very quickly. And then the last one is a milling cutter. That is, it's a face mill, so it's cutting on the top surface of the material. So what I want you to do is I want you to think about which of the material properties are most important for that application. And it will always be more than one, and you could argue for many of them. But try to think of the ones that would probably be most important for that application. And this is in groups of 2 or 3. If you don't want to work with somebody at your table, you
I'm really
can
awkward with
move.
you guys.
Oh, then we don't either.
Who's playing on the phone?
No.
Yeah, because my partner,
Charles, do you want to write it? I've got a behind.
These are all the things. No one's in.
We're the only ones called that.
There we go. So in looking at this, that's what I really wanted. What kind of material properties did you think for the injection screw? What do you think is most important?
You said thermal conductivity because the screw is part of what is not in the plastic.
Okay, so there is some level of thermal conductivity. The screw actually doesn't get heated on its own.
No, but the shear that it's making is helping keep the plastic.
Yeah, the shear does heat the plastic, and so it's actually a little bit better if it doesn't conduct too much heat, because if the screw conducts too much heat, it's going to be pulling heat out of the plastic, and we don't want that. But it turns out, in either case, we don't do much about the design for thermal conductivity. It ends up, it's hard to think about this, but the thermal scales of these two are so completely different that the metal really doesn't care about the thermal condition of the plastic, because it's hundreds, if not 1,000 degrees lower.
So all of those thermal properties wouldn't necessarily be taken into consideration?
They would be taken into consideration, but they're all secondary concern.
Yeah.
Yeah.
So,
Sorry, I should not laugh at you.
We said yield strength, because you don't want your screw to bend.
Okay,
or have
so
the flanges bend.
there is a bunch of pressure when you do that injection process, and the piston pushes this forward to inject the material. So you do have to make sure that it's not going to yield. You don't want to shear those threads right off there. So yes.
Hardness, because it's like rotating and rubbing against the barrel.
Yeah, it turns out, oddly enough, you would think if you took plastic and you rubbed it against a piece of metal that there's no chance that it's really going to damage it. But hardness is the one key characteristic of an injection screw, and that's because it will just get eroded by that constant, very heavy shearing action that is going on. And so it's not intuitive. At least it's not to me intuitive that that would be the thing that matters. It is doubly or triply or quintuply or beyond that true if you're doing something that is a filled material. So if it has any higher melting temperature filler, and especially if it's got stuff like carbon in it, that's just brutal on screws. And so hardness is the chief one. We need to understand the strength really well, and we need to take into consideration the thermal ones. But because they're on a different scale, they don't tend to matter very much. Not intuitive. Oh, I am on the wrong screen for being able to do this. All right, so taking a ram, shoving an amount of aluminum or some other material through a die. What do we think is most important for the die? Yes?
Is it toughness?
So it's toughness if your control system's not very good. If your control system's not very good, then this ram is going to come in here, and it can also be if if you don't control friction very well, because then you start pushing on this billet and it will slam into the die. And the die is in a bit of a weakened state because of the temperatures that are going on here from the friction and maybe from the heated material. So toughness can be. That's actually why this die has this giant die backer on here. The die backer is not as strong a material, or not as hard a material, and so it is a much tougher material just to absorb that energy from the die so that the die doesn't have to absorb the energy on its own.
What is the control system?
So if the control system that's pushing the ram forward, so when you put the billet in there, if the control system isn't smooth, it will slam the die, the billet into the die. Yeah, and so it'll push it in there really hard, and sort of it has this big shock that it has to endure. If you have a really good control system and you have a good way to control the friction, the other thing that can happen is if you have a lot of stick-slip friction where you push it and it sticks and it sticks and then it slips and it sticks and it sticks and then it slips, that can also cause a lot of pounding on the die. So they do all kinds of really cool things with it. One of them is you take your aluminum block before you put it in there and you roll it in shattered glass or in glass powder. And then when you put it in there and you start compressing it, the temperatures will melt that glass around the outside, and it puts this little layer of liquid that keeps friction from happening between the two. Pretty
It's
cool.
like kind of like a lubrication.
Yeah, it becomes a lubrication, and then at the end you can just break it out of the inside and use it.
Wow, that's
Awesome.
really cool.
Yeah. Okay, what else is really important for the die? Yeah.
Surface condition.
The surface condition, okay. It is something that is under a lot of tension when you are pushing on it. It is trying to break it out, and so if it had any cracks in it, they would try to propagate. It's true. What else?
hardness?
Hardness, again, we are shoving a metal through a metal, and so if the plastic could wear the metal, then this certainly can wear the metal, and it will erode the die, and then you have to replace the die.
I think thermal conductivity, because it heats up really fast and might form things.
Okay, it can be, I think. So we, of course, at this point in the class don't have any context for this, which makes it a little challenging. In general, the material gets pushed through the die in a matter of seconds. So it's probably like 30 seconds for a 6-foot billet to be pushed through. So I'm not sure that thermal conductivity ends up being that important just because it's not in contact with the heat for that long. Yeah. But it could be that it has to conduct it away. In the end, the materials that they use, they have to get the strength of those materials to be sufficient, and the really high strength materials have poor conductivity, and so they lose out on that. It might be something that they would like to have more, but they lose out on it because of getting the strength that they need. Okay, let's talk about well, let's see, for the, I don't know, the billet. The material that you're squirting through the end as a solid. It stays solid the whole time. What do you think matters for that? Yeah.
Ductility, or I guess rather lack of ductility.
You'd like to have ductility, yeah. So you'd like to be able to reform the shape of this as much as possible. And so we measure the ductility. We talk about reduction in percent area. This is way outside what we could normally do. And some of that is because we have it in compression all around, and so it keeps it from cracking, and some is because we heat it. But this is a huge amount of ductility. We would also like the yield strength of this material to be relatively low, so we can shove it through the little hole in the end without having to generate too much force. What about these cutting inserts? Yeah?
Hardness?
Hardness, okay, so definitely hardness, because they are deforming another material out of the way. They are scratching and indenting and clawing their way through the material. So yes, hardness matters.
Toughness?
Toughness matters, because they come around and they smack into the edge of the material. Now there's a problem. Hardness and toughness almost never go together. The harder material is, the lower its toughness usually, because it becomes a brittle material and it doesn't impact or it doesn't absorb the material very well. So they do the same thing here that they did on that die backer. So there's an insert, and then right behind the insert there will often be another little thing that looks like an insert. And so what they're doing there is the insert itself is a very hard material so that it can deform through there, and then they will back it up with something that has better ability to absorb that energy. So it has a better toughness to it. And then the combination of the two, one of them provides the hardness to cut the material, and the other provides the sponginess, if you want. It provides the ability to absorb that energy so that the cutting inserts can survive. Yes?
We also said surface conditions, so if any of the cutting inserts have like a little tiny crack, then it could just fail immediately.
Okay, yeah, so the little tiny cracks will cause them to fail. That is absolutely true. Oddly, this is a place where thermal conductivity matters a lot as well, because it generates a hellacious amount of heat right there at the end. And you have to try to get that away from that end as quickly as you can. Otherwise, you will weld the material that you're trying to cut to the end of the cutting tool, and that doesn't make a very good cutting tool when you've welded something to it.
This sounds super ideal.
Yeah, happens a lot. It's really easy to do. Yeah. Yes. Happens. It's the primary failure mechanism of many cutting processes is that you weld on material. All right.
You'd think they'd fix that by now.
It's hard. You can fix it, but you don't make any money if you do, because you're machining so slowly. So it's always a balance. All right, well, there is day one of material service attributes, and we will have 2 more days, but they're spread out over time this year. So I will see you on Thursday. No, you can keep that. Everybody was here and did a good job.
I'm gonna throw it away if I keep it.
Okay, well, I'm gonna throw it away if I keep it.
I'm so bad with this.
Sorry, it's not me here with handout.